We're going to continue now with looking at supervised learning, and I want to consider two of the sort of fairly famous techniques that are available to us, famous in the sense that they were widely used in industry. The first one is classification trees. The second is support vector machine. We're going to start with classification trees and look at a little bit of how the algorithm works. Again, just like all of these algorithms, they're typically iterative structures. They're principled ways to look at the data that you're going after. And so we're going to consider this here first in sort of a high-level view, and then later we'll go through some code base to show how this actually can be implemented in practice in a variety of tools. Mostly we're going to be doing this in Python, but of course this technique is so ubiquitous that it shows up in almost every commercial package available. So let's start off here. This is a supervised learning technique, and these are classification trees, and we're going to call also leading to what are called random forests. And so this is a way to search through your data, labeled data. Remember, you're going to be given data that already has a set of labels. Your task is then to build a classification. So in other words, I train it on a data set, but I give you now new data, and with that new data, your objective is to provide labels for the outputs. But given that you have a supervised learning algorithm, it means that you started off with some data that already had labels. So you already kind of know a bit about the data in general. So let's come back to this structure of the supervised learning task. Okay, so first of all, the way we have this set up is that we have data and we have labels. The data itself are these x of j. It's an n-dimensional data array. Okay, now this is going to be really important because each of those n dimensions are going to be dimensions we're going to search through in order to start looking to see which one of them could we use to make classification happen. So I have m total data points. This vector x now is going to play a profoundly important role in the classification tree because what we're going to do is search through x for making splits in our data. And in fact, classification trees are kind of very simple. What it's going to do, it's going to be a routine, it's going to be an algorithm, it's a loop through each of the x of j, okay? The first time through, it's going to look through all n components, and what it's going to do is component by component and ask the following question. If I look at x1, which is the first component of this vector, and I ask the question, if I were used to use x1, and I were to say somewhere in x1, I'm going to make a decision. In other words, x1 values above this value give me a label of 0.1, and below this give me a value of -1. How well does it separate the data? So this is the idea. Make a split at the best component for classification. So I'm going to try it first for x1, then x2, then x3, all the way to x of n. So I'm going to scan through every single component, scan through it, and ask the question, what is the if I make a decision here and split the data somewhere here to make a classification between these labels, how well do I do? Okay? So in other words, you could imagine for each one of these, so for x1, maybe you find, oh, my split gives me only a 50-50%. But x2 gives me a 70-30%, 70% accurate. And then split x3 gives me a certain percentage. I can scan through all of it and ask who has the best shot at splitting the data. That's where I'm going to make my first classification cut. And then I have n-1 variables left, and then I'm going to go through each of the other variables that are left over and say, now, if I make a second cut, which variable gives me the best capability for doing a classification task? So this is a very expensive routine, right? So I am starting off along all n dimensions here, and n could be quite large, right, in practice. So if n is quite large in practice, I have to go through each one. I have to scan through all of the data and ask the question, where's the best place to make a split? And then I have to do that for all n variables across all n data. So this is very expensive to do. And once I pick the first variable to make the split on, then I have to do it again now with the remaining n-1 variables. And then once I make another split, I do the n-2 variables and so forth until I've made essentially a classification tree. Now, Part of the reason we talk about random forest is if you just do this technique, if you have data with noise, when you start going a ways down this tree, it becomes super susceptible to noise fluctuation. So your data itself starts to create very different tree structures. So random forest allows us to sort of think about shuffling that and making sort of more probabilistic trees out of this structure. So that's the mathematical architecture. I want to demonstrate this on a simple example where x here is only 4 degrees of freedom. So x itself has degree 4, so you're only going to walk along 4 variables. So the reason we want to do this is because I can actually show you the results from beginning to end. Okay? And this is the iris data set that I had shown earlier. So here's the iris data set. And I'm projecting along, there's 4 components of the iris data set. There is the sepal length, sepal width, petal width. And so what I'm going to do here, they're called x1, x2, x3, x4. Those are the 4 components. And I'm projecting all the data onto those 4 components. This is projecting x1, x2, and then x3, x4. Okay, and here's what those components are. And so what I'm going to do, here's how the algorithm works. The algorithm is going to come down here and say, okay, let's look at x1. By the way, x1 is sitting right here, right? This is the x1 variable. And then this is the x2 variable. And then x3 is here, and x4 is here. So I'm going to go through each of these variables in turn and ask the following question. If I were to go along one of these variables, what's the probability of splitting my data in the best way possible? Right? And then I want to split it there. So notice if I walk along x1, look at this. If I walk along x1, I can get a perfect split between the magenta and the green and blue balls. In other words, it's almost like I can get 100% accuracy in splitting it along x1. If I come along x2 here, it's still not bad. I don't get quite the same separation between the magenta and green. So I could split it along here as well, but it turns out, you know, this gap between these two is quite a bit bigger. So this is the best split point. x3 and x4, if you split along there, you can see I don't really get good splitting of the data overall. So my first split is along x1. This is called split 1 right here, this line right here, which basically is equidistant between where the green balls are and the magenta balls are. So you split the data right there. Okay, that's my first split. Okay? I now have the ability to walk through all the variables again and say, where do I want to make my second split? And so now my second split is to say I've got a region here of X, this region, and I have this region. And so now in each region, I start doing the splitting. So look, in X1, I don't have to do any more splitting. Just splitting along this X1 direction, I get this magenta group just all by itself. It's like a perfect split. So I'm done. I don't have to split this region anymore. But over here, I have these 2 data sets I'm trying to split out, the green and the blue. And so I can split either along this direction or this direction, or I could split along x3 and x4. But you can see, if I'm trying to split the blue and the green over in x3 and x4, they're just overlapping each other. So it's a bad split. But over here, what it finds is that the best way to split the green and the blue is along this line here. This is split number 2. So this gives you the best separation. In other words, the most accurate separation. What's the accuracy of splitting? Like if I label the data, I get 90% of them right, 95% of them right, whatever the highest accuracy. This is the best accuracy I get is along split number 2. I now have 2 regions, above this line and below the line. Now above the line is just blue balls, so I don't have to do any more splitting there. I'm done. There's no more splits to be made. But now below the line, I look and I have 2 regions. There's sort of like the blue and green balls down here. And now it looks to say, well, let's again split along this direction. Should I split this way or should I split some more? And it says, look, split number 3. This is the best separation line where everything here is green, or gives you the best separation to green on this side, blue on that side. So with 3 splits, I actually have a classification of the data. Okay? So this is only 4 variables. Imagine if you were doing a classification tree with 1,000 variables, 10,000 variables. You'd be doing this in massive scale, okay? And what you'd actually end up getting then is a classification tree. So all of that splitting architecture, which you're seeing right here in practice happening, this is very visually appealing, hopefully, that you see this and how the splitting is happening, it's interpretable, is that what you would see is that this is the return that you would get from one of these classification tree type architectures. It would start at the top and first give you the first split. There it is. Here's my first split. This is the values that I would be splitting on. So if x2 is less than something or x2 is greater than something, that's where I split. Okay, so let's go back and look at that graph here. So remember, I'm gonna split along here. So, so this is my first split. And so see what this value is? Actually, this here is x2. I sorry, misread that. Or actually, this is x3, x4. I think I mislabeled this. This is x2 here. So this is a value of about 2.3 or 4. And in fact, you can see it here. It's actually 2.35, actually. So if the value is less than 2.35 or greater than 2.35, that's where you do your first split. And then this here, it's just done. So on this side, we didn't have to split anymore because we got all the magenta balls in that one group. So it terminates the tree right there. No more need for splitting because there's only one class left in that bin. So you don't have to do a classification at all. Now the other side of the bin gives you the second line, which is that horizontal line. And here's where that horizontal line, 1.75. That line separates now blue on top, green on bottom. The blue on top is by itself, and that's why you don't have to split it anymore. But then the bottom box had greens and blues together, but there's one more split here, which once you do this, you kind of separate those green and blues. So this is what a classification tree looks like. Presumably the idea here is that once you have this, you can come back and look at these features. X2 would mean something, right? X2 is actually meaningful in terms of, in fact, all these variables you're splitting along are things like sepal length, sepal width, petal length, petal width. So these are very interpretable quantities. You're saying, oh, if I have a petal width above this or a sepal width below that, that means it's this kind versus that kind. So that is sort of an interpretable structure that comes out of this. And this is kind of a generic thing that you get out of a classification tree. So again, what you're looking at here is if you do this at scale, right, then this can become very large for you, right? Here, there's only 4 features in this data set, which are the sepal length, sepal width, petal length, petal width. And so here, it's very interpretable. I can draw a nice little diagram like this. But if you go to scale, it's much more complex about where all these splits happen. But still, you can come back to this and start thinking about, is this meaningful in terms of the initial problem that you would have had with it? And it's this architecture like this is the basis for all of these kind of algorithms. We can also apply this to the dog and cat problem that we've already been playing around with throughout this, right, in this principal component space. Same kind of thing. Here's how you separate dogs and cats, right? So if we were to do this dog and cats along this low rank projection space, PCA 1 and 2, you ask the question, how well do I separate that in terms of the PCA space? And here's what you're getting. These are the splits that you have in terms of setting up a tree architecture. And of course, sometimes you can continue the tree, right? You can keep splitting it more and more finely, but at some point too, you don't want to split it so finely. They're just some dogs and cats that look very similar in feature space, and you don't want to like work so hard to separate things that aren't actually that separate. But this is sort of what a classification tree would look like coming out for the dogs and cats. And that's what you're looking to do here is this kind of structure. One of the things that we'll consider later when we do coding is one of the top algorithms for doing random forest and very stable, robust classification trees is XGBoost, which is sort of, I would say, is the leading algorithm for to do these kind of classification tasks with a classification tree. And we'll cover that later, both in the code and a little bit in terms of the theory of it. Other than that, I think that's just an interpretable way to kind of get at this supervised learning algorithm. And again, classification trees, along with support vector machines, were the 2 workhorses of the machine learning industry. So here in Seattle, where we live, if you knew one of those two algorithms, this is what a lot of the tech companies were using in machine learning before 2014, when we have the advent of neural networks and sort of a transformation in terms of a tool set we could use for doing analysis of data sets.